Hello, everyone. This is Junbo, and today I'm going to present locating everyday objects using NFC textiles. And this work is done together with Jingxian, Ke, Chengfeng, Carmel, and Swarn. So seeing the title, we have NFC here. What is NFC? It stands for Near Field Communication. In recent years, we use NFC a lot for access, for payment, and for attendance tracking. And at the same time, we're also having an increasing number of NFC-enabled objects around us. For example, keyfobes, credit cards, smart devices like smartwatches, smartphones, you name it. It's becoming more and more ubiquitous. However, on the other hand, most of these applications are limited to only communication. If we compare NFC with its dear brother, RFID. So RFID has a lot of sensing applications enabled by localization techniques, such as device tracking, human body frame sensing, etc. So in this paper, we ask a center question here. Can we bring some localization flavor to NFC as well and enable some fancy sensing applications, just like its dear brother RFID? But as soon as I raise this question, something just comes to our mind. And that is, as a known fact, the commercial NFC typically works within 5 centimeters. And actually, we do see some previous work that tries to bring some sensing flavor to NFC, but most of them are limited to proximity sensing rather than real localization because of this comfort zone. So therefore, the first question we ask here is that can we extend the range a little bit? And also in addition, we ask another question here, and that is, can we have a larger surface area to play with? For example, can I make my whole table, my bed, my couch, my chair NFC enabled? Is it possible? So actually, we have some candidate solutions to try to extend our range a little bit. For example, we can use some long-range reader antennas, maybe. They're usually efficient and tuned to have a high resonance at NFC frequency. But on the other hand, they usually come rigid and bulky. On the other hand, we can also use relays. They're quite simple, but sometimes it's just so inconvenient for us to carry them. And most importantly, both of these lack the localization flavor. On the other hand, we do see some 2D localization work using arrays of simple NFC coils. And this solution is quite straightforward, but it requires hundreds of those coils. And most importantly, it's range limited on the third dimension and also unable to do 3D localization. So now we have our goal quite clear. We want a little bit more range and a little bit more localization flavor. So seeing all the background here, we present our solution, Textile Sense. And this is our first step trial to bring some localization flavor to NFC. Textile Sense has multiple textile coils that are flexible, so they can be mounted on irregular surfaces like this. For example, I mounted on my couch, and then I turned into this a smart sensing furniture. So why is it smart? Because it's able to detect and localize both NFC tagged objects and untagged conductive objects. And the maximum detection range of Textile Sense is 20 centimeters. And also it has a centimeter level localization accuracy. So what is the secret sauce behind Textile Sense? Actually, the first one is blind near-field beamforming, which helps Textile Sense to extend its range. And the second one is data-driven localization, which helps Textile Sense to locate the objects. Now, actually, there is another important module, system calibration, and we will refer to this later. So let's just first dive into the first secret sauce here, the blind near-field beamforming. So beamforming has actually been well known for improving radio coverage and enabling advanced location tracking. And a very simple and intuitive interpretation of beamforming is just the coherent combining of signals. Suppose we have two senders and they're trying to send a signal X to the receiver. Our goal is to try to maximize the received signal strength here. And as we all know that the signal will suffer from attenuation and also some phase shift during its propagation. So the worst case is that we get nothing at the receiver like this because the signals, they just destruct with each other. However, what if we shift the signal a little bit before we transmit? Now things are different like this. And this is exactly what we wanted. So in practice, we multiply the signal with something called a beamforming weight. And as we know, in traditional beamforming, the signals are usually voltage, and the optimal weight is usually relating to the corresponding channel H here. So now, how does it work under NFC? Is it the same? Not really, to be honest. So to understand this, we need to dive into the underlying physics of NFC, and that is magnetic coupling. So you might have been familiar with this animation where we have a source coil and a load coil. The source coil has a change in current IS here, which will generate a varying magnetic field visualized by the green lines. So now if we put a load coil nearby, there will be a current IL induced in the load coil. And actually both the IS and IL, they're changing, so they will influence with each other. And this mutual influence is captured by our circuit here. So in fact, NFC uses current to carry important information. So it's important for us to bridge this IS and IL. And the bridge here is the small m. We can also call this the magnetic channel, or maybe the near field channel. And actually you can see that it absorbs the frequency omega here, the capital M, which is the mutual inductance, and also the impedance of our load. So for near field beamforming, now the signals are current instead of voltage. And also we need to construct the beamforming weights with the corresponding channel M now. But is it done? This is not the end of the story. We are now in a trouble. Actually, where? So let's consider a team of textile sense coils trying to beamform to an object of interest. The coils will ask you, hey, we know nothing about the potential objects. Where shall we beam to? Right? As the coils, they will never know when or where you might put an object of interest. And we refer to this as the blind near-field beamforming problem. And actually, the blindness comes from two aspects. The first one, as I mentioned, we need to detect the presence. But even if we know that there is something, none of these channels, M1, M2, they're known. So at the first glance, you might say, hey, these are just circuit parameters. Let's just measure them, right? For example, keep coil 2, 3 until N open and apply some known voltage on coil 1. So measure some current and do some calculation on M1. And then maybe let's only turn on coil 2, leave other coils open, and then calculate M2. Do something successive. So however, actually in practice, there are two reasons that prevent us from doing this. So the first one is actually, as I mentioned, the channels here not only depends on the mutual inductance, but also the impedance of the load. So do you ever gonna know the impedance of your credit card? Not likely, right? And the second reason is that, as I said, we can finally achieve 20 centimeter with this system. And now we are turning off every other coil and leaving only one coil on. We just fall back to that comfort zone, right? And we have nothing done. So we really have to consider something indirect and leave all the coils on all the time. So for the discovery part, actually, we leverage an important observation here. And that is the receiver will couple with the transmitter in the near field. And this is quite different from the far field case, and we can make use of it. Specifically, this is saying that the weak coupling between the object and the coils is effectively imposing some unknown load on the coils. And said differently, if we monitor the voltage across the coils, now, if there's something nearby, we see a variation in the voltage. Although we cannot really measure the channel, we can see this variation. Therefore, we can keep measuring the voltage across the coils. And then if we see a variation, we know that potentially there is something. And then we can do something next. And what's next? It's going to be the actual beamforming. So in this stage, we also leverage another important observation. And that is, if the optimal beamforming weights are applied, then the sum of the voltage squared across all the coils should reach a minimum. And the intuition behind this can be illustrated by the energy bars here on the right. So what does the optimal beamforming weight do? It actually tries to deliver a maximum amount of energy to the object. But if I do that, then effectively I'm trying to reduce the net energy as much as possible. And the sum of the voltage squared across all the coils actually serve as a good indicator of the net energy here. So now we have the whole chain. Actually, the voltage measurement is an important feedback on the weight's goodness. So the lower the sum, the better the weights. And we can actually formulate a problem like this. So messy math, right? But actually the intuition behind this is quite simple. That is, the optimal beamforming weights are trying to minimize the total net energy. And the total net energy is represented by the sum of the voltage squared here. And we can solve this problem with some standard gradient descent methods. So now we can briefly talk about our second secret sauce, and that is data-driven localization. So at a high level, it is a fingerprinting approach. Therefore, we require this system calibration before our actual application. And this is a one-time data collection. So we don't really have to worry about that anymore later. So in the far field, if you remember that we usually have a nice mapping between a beamforming vector and an energized position, because we can make use of the far field free space propagation and power law fading models to estimate the signal strength. But now in the near field, we have the messy, complicated coupling between, for example, between TX and RX, or even among transmitters. So therefore, this mapping no longer exists, and we have to consider something indirect. And our approach is that we try to map the voltage measurement directly to the object's location. But of course, this voltage measurement is what we get after we apply the optimal beamforming vector. And that is to say, we try to map this voltage vector to the position vector. And at a high level, our model is the simplest nearest neighbor model. And we also process our data with the least square, curve, and surface fitting techniques. So I will omit the details here in the interest of time. So please refer to our paper for more details. And also, if you're interested in multiple objects or textile coil design, please also read our paper. So now for the implementation, actually, as I mentioned, I mounted the coils on my couch. We also have our system components shown here. Basically, the RF detectors and the Arduino board, they are used to measure the voltage. And we obtain the ground truth with a laser rangefinder. We consider 3 different kinds of objects in our experiment, and we have 2 baselines. The first one is a single coil baseline. It's just a single large coil with the same total area and the same transmission power. And the multi-coil baseline is just Textile sense, but without beamforming. And we will see 3 experiments here today, but feel free to discover more in our paper. So the first experiment is about object detection and localization. And we use 3 different kinds of objects. So it's quite obvious here, right? Quite obvious that the baseline is floating above our Textile sense, which is good because the lower one is a better one. So in details, actually, Textile sense has a longer detection range. For example, for NFC tags, it can achieve 20 centimeters, while the baseline is only 12. Note that both our systems cannot localize anymore beyond a certain range limit and can only do detection at that moment. And that's where the curve will end in this figure. And on the other hand, we can also see that our Textile sense has a lower localization error if you see the error bars. So the conclusion here is that the voltage measurement across the coils, they will only serve as a good indicator of the position if we do beamforming. Otherwise, they seem random and they just do not provide much insight. And the second experiment here is about object orientation. And we compare Textile sense with the single coil baseline. And we only use NFC tags here. So now the big trend is that the performance will degrade for both the systems, but still we achieve a nearly 2x better detection range compared to the baseline. So the conclusion here is that with equal transmission power, Textile sense is the better one. Finally, we have the textile Bendy and coupling experiment, and we compare Textile sense with itself. And also we only use NFC tags here. Note that the system is calibrated under the bending scenario because it's more practical in our real application. But we evaluate both the bending scenario and the flat scenario. So the latter one is actually not calibrated. So from this figure, we see that Textile sense is able to adapt to some shape change without a huge loss of performance. Of course, there are more experiments to go, and feel free to read them. The system, of course, is definitely not perfect at this moment. This is just our first step trial, So specifically, we cannot really deal with the strong coupling between 2 objects, for example, 2 closed tags. And also the system cost, it's really high at this moment. We're using USRPs. So in the future, we see its potential to be constructed with a commercial NFC reader and the phase shifter. So we can buy them online, maybe. So we actually have a detailed discussion of our limitations in the paper. Finally, here we show some potential applications. So for example, here I'm using my hand to control the volume bar. It's kind of like a fine-grained tracking of my hand. And also I can use my hand to control the room light. It's like turn on the light and then turn off the light, something like that. So yeah. And the second one is the object localization. So for example, if I tag this object, then we can track its location, just like this. So finally, we can even do some pose estimation, for example. Now, if I sit here, it will say, okay, this person sits and then turns on the light. But what if I'm going to take a nap? For example, I just lie down. It will detect my leg and then says, okay, this person lied down and turns off the light. So to conclude, today we see Textile sense. And we briefly talked about its secret sauce as shown here. It uses near field beamforming to discover objects. and deliver a maximum amount of energy. And then it will use a fingerprinting approach to localize the objects. Feel free to see our website for more details. And thanks a lot.